Sorry to interrupt you, Maya. The people online cannot hear you because you're on mute.
Unmute. Okay.
Okay, now we
Okay,
can.
so
Do you mind just restarting your presentation?
restarting the presentation. Okay. I hope there are
Thank
lots
you.
of people. So this time it's going to be quicker, right? So Forever Kotlin Plan is the title of the talk. It's about imperative, declarative, object-oriented, and functional. Those are the main topics. Who am I? Maia Grotepass from Luno. Why am I giving this talk? It's because I see these words all over. I think I know what they mean, but I'm not sure what they mean. So I thought I'd go and research them. So I covered you with a disclaimer. I come at this from an engineering perspective, not a computer science perspective. So it means the dates are not going to be 100% and maybe the definitions aren't going to be spot on. The opinions are my own. And this is my language history. So this is where I came from. Basic, Pascal, machine language, C, C++, some Bash, Python, maybe some Perl, Java, a lot of time in Java, a smattering of Scala for a brief moment, and then Kotlin. And the other thing to know about me is I'm a mobile dev. I work on Android, writing mobile apps on Android. So let's start off with imperative. So what is the definition of an imperative language? The definition is that it consists mostly of a series of commands. Okay, so a bash script, imperative, probably. So on the right-hand side there, you'll see I have a sample of a function that has some imperative code in it. It's Kotlin. It might look unfamiliar if it looks familiar, but what you need to notice is that there's a for loop that loops, there's another for loop, there's an if, there's some variables, we're setting some variables, we're reading some variables, and all of this is wrapped in a function. The function isn't the declarative part, it's the part inside here that's declarative. So now, let's take this diagram. So what this diagram means is these lines over here, these are the commands. So it's an imperative language. It's a sequence of commands that are happening one after the other. If it were machine language, there would be some program counter that makes it go from the one language to the next. This blue cloud you see here, that's the state of the code. So like, is it in an enabled state? Is it in a streaming state? Is it in a muted state or an unmuted state? So it's program state. It's memory. Now, I know in a computer program, there are other pieces of memory. There's stack and there's heap. But for the purpose of this talk, that blue cloud means the state of your code. And we change the state of the code with the commands, and then we do different things depending on what the state of the command is. This is like an abstract view of how computer languages work. So you can write, this would be like if you're writing a variable value, and this is if you're reading a variable value. And then for an imperative language to work, you also need some other conditional. So this would be something like looking if something is true. There might be something say, is she muted in here? If it's true, then jump to this piece of code. If it's false, then do the things inside here. And with these conditionals, you can actually construct loops. So that's what you need for an imperative language. There's another piece to this, which is called a side effect. Typically, when they're talking about these languages, a side effect is something like a print line or writing to disk. It's not part of this description of the paradigm of the language. Now, we all need those side effects because otherwise, how would you know what's happening inside of the program? But they're typically dealt with as a separate thing, separate from the main paradigm. Now, if you're coding in a language like this, what happens? This happens. So if you have lots of these commands and you're reading and writing to one global piece of memory, and you've got these ifs and fors and loops, this is what happens. And then if you look reading machine language, that often happens, and that's the thing. And even if you're writing some simple language like C, this can quite often happen. Someone starts writing a function, a method inside an object, dare I say, and they start writing in an imperative way, and it actually ends up looking like this. Now, humans have a memory stack of about 4. So we've got a working memory. We can keep 4 things in our mind at any one time. Some people can do more, some people can do less. So just think about your phone number. If you say your phone number to somebody, you usually say something like 021 556 8003. So you're breaking that up into pieces because our memory can't deal with a thing like this. Our memory can't deal with all of those, keeping all of that state in our head. So the other thing about humans to know is that we're really, really good at pattern matching. So we'll see a big mess of all of these commands, and we'll start looking for some patterns because we're trying to make some pattern that makes it easier for us to fit all of this in our head, because it's super, super difficult to debug this. Even with the debugger stepping through, you're actually in parallel trying to keep that blue state of the program in your head. So what happens then is we start seeing, okay, these lines look like these lines. Okay, so that's the same thing. Maybe if I can just make a way to collapse this so I don't have to read through all of this. And then what happens is we start making functions. So then we're now in the world of procedural imperative languages. So what happens here, these lines that were over here, they get pulled out into a function, and over here and get pulled out into a function. Now you could do it one of two ways. Either you could pass the state in here into this function and then just get the state out so that this function doesn't touch this big blue cloud at all, or you can keep accessing the big blue cloud in this function. So there's the two different ways of writing a function. So now into Kotlin. So another piece of this talk is that I really love Kotlin. And so what I did was I had a look at the Kotlin language, and I picked out features in the Kotlin language which would make any of these kinds of paradigms easy to use. How is the language supporting me to be able to think and work in an imperative style? So I'm going to start with imperative. This part I'm going to go through reasonably quickly because I think you all know imperative really well, and so you're comfortable with that. So Kotlin has variables. Obviously, this is the writing into the big blue cloud. You can have a variable that can't change. So if you set it once, this is pi, it doesn't change. Or you can have a variable that can change. There, I'm setting it over there like that. And here, the other concept that they have is if you put a question mark at the end, it means the string can be null. Now, you don't need to remember any of this code. All of this code comes either from small snippets of samples that I have or from the Kotlin Lang website where all of this is explained. And also, this is not a complete view of the language. It's just the pieces that I like that make this paradigm easy to use. So we had, if you remember, we were writing to the big blue cloud. We had variables. Now, the other thing you need is a conditional. That's that green diamond where you need to decide the one or the other. So we have conditionals. Predictably, this looks like Java. If something, something, else something. The nice thing about Kotlin is that this conditional statement is also an expression. So you can set it to a variable. This outputs values that can be set to a variable. And this when is just like a switch statement. It's a big if-else breakdown conditional that has all of these options. So this is just the syntax of how that would look. And then, of course, there are loops. We all love loops, for loops with all sorts of ways of going up and down them, a while loop, and there's a do while. The interesting thing about the do while is that this while variable that you see over here, it's actually scoped so that you can access it with inside the do. So you define it over there and then you access it in the while. So pros and cons of imperative languages. Imperative languages somehow are easy to grasp for me. If you think about this is what the machine's doing and it's easy to code in that way. The con of an imperative language is messy spaghetti. Quite easily. You only need like more than 15 lines of code and it can turn into spaghetti. And the state modification, that's what you change in the blue cloud, and the behavior is very much intertwined. You're checking the state, you're changing the state, you're doing behavior, and all of that is kind of meshed together. So the next paradigm is the declarative paradigm. Oh, what I forgot to say was the imperative language comes from machine language, which is quite old. But the first sort of language that was using imperative language was Fortran. Now, the dates are difficult to find, but I think the data found when the first compiler was there was about 1956. So it's got quite an old history. Now, declarative, the way they define it is typical programmers. It's the opposite of. So a declarative language is a non-imperative style, right? So that means it's not a sequence of commands. In which a program describes what the desired results without explicitly listing the commands or steps that must be performed. So that was kind of difficult for me to think of a good example, like how would I tangibly think of a way? And the first example that comes to mind that's actually easy to grasp is something like HTML. So HTML just says what's on the page. There's an edit text maybe, there's a button. It says nothing about the behavior, it says nothing about the state. The behavior and the state are not gone. They're just not there. They're just not part of the declarative part. They're sitting somewhere else. So here we have an example of Kotlin code that's declarative. This is an extract from Jetpack Compose. So this is Google's UI library. And what we're saying here, this is a function that gets called, I want a card. If the state is that it's face up, I want to show its picture. If it's not, I want to show the back of the card. So there's no behavior. If you click on the card, which is the behavior, it actually just calls a function out. So that's not part of this piece. If it's face up and the suit is the state that's coming in here. So you can see I'm saying what I want, but I don't deal with the state and I don't deal with the behavior. So this is the picture for that. We have some other, UI is a good example, but it doesn't have to be UI. It could be other things that you want to declare in a DSL. So a DSL is a very good example of a declarative language. You just say what you want, and then you let some other piece of code somewhere else deal with the state changes and the imperative. You can't escape this because a computer program has to have a state of some sort. And you can't escape some of the imperative pieces, but this is just a separation. And why do we do those separations? It's that thing because our brains can't have all of that code in our brains at one time. So we're making the separation so that we can think about what the UI would look like separately from worrying about the state. We don't care how the card got flipped or what happened. We just care about how are we going to represent that card on screen, say, depending on the state. Now, the other thing to mention about declarative systems is that there's usually some other framework in between. There's usually some other, there's JavaScript that handles the state and the behavior, but there's some other framework like HTML that sits, that provides that, or Jetpack Compose that provides that declarative framework. Another example is something like RxJava, where you've got all of these functions, they're being called, and you can do different transformations, and you're declaring what transformations you want without saying exactly how they happen. But there's a framework behind a declarative language. And the history of a declarative language, well, that's actually very interesting. So it comes from Lisp, the language which is just 1 year younger than Fortran. So it's been around a long time, where the imperative languages came from something like machine language, the commands in the machine. The declarative frameworks actually come from the 1930s and come from Lambda calculus. So in a weird way, the declarative languages are way, 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 way older than the imperative languages, because the imperative languages only came when people started having processes that they needed to control. And in a way, this is understandable because the humans are trying to make systems to understand, and a declarative language is just another system that's built on top of an underlying system. Like Lambda calculus is built underneath there's mathematics, but the Lambda calculus is a way to represent concepts in a short and succinct way. So how does Kotlin support declarative languages? Now, if you want to make your own declarative language, it would be something like a DSL. Or if you're using something like Jetpack Compose or any of the others, they use, these are the language features that make it easy to use declarative languages. So this little snippet here is a simplified example of the Kotlin standard libraries. So the Kotlin standard libraries is also declarative. You can use them with collections. And this is just an example of what a map function would look like. And the thing to know here is that what Kotlin did was they said that functions are first-class citizens. That means you can pass a function in as a parameter. So this piece of syntax over here says, I've got some other transform function. It's a method or a function that takes in an integer and spits out an integer. And then this function will use that over here. So it's this piece over here that makes it easy to build declarative languages, the fact that you can pass a function in as a parameter. And then how would you use it? Here I've got a list. It's a list of integers. Here I'm calling this my map function. And here, so the other thing that Kotlin has is that if the last parameter is a function, you don't have to call it within the round braces. You can pull it out and put it in the curly braces like that. So that's functions as a parameter and the way that they pull out that function in the syntax. The other thing they have is that as the concept of extension functions and infix operators. So an extension function is they have an int object, but I want to add a new operator to int because I'm dreaming up some new operator on int. The operator is called my plus. And this means this is another method that you can call on top of int. And this infix means it doesn't have to be called like a normal method. It can be called like an operator. So when you're using it, you would use it like this. This is an integer. This my plus is an extension function like that on integer. And because it's an infix function, it means the function can be in between the thing that it's calling on and the parameter that's coming on the outside. And then the other thing that Kotlin has, which is great for declarative language, is this var arg keyword. And what this just means here is that I can have an endless list of these TS parameters coming in. Okay. Pros and cons, declarative languages. So one of the pros is definitely that there's that separation and that you can reason about the piece and the declarative part separately from the imperative and the state pieces. And also you can define a consistent way of handling state and behavior. So an example of this would be in something like Jetpack Compose, there's the unidirectional state flow pattern. I think React patterns also have that. So you can decide, we will always send our state in like this, and we will always deal with behavior like that, so that you have less of that spaghetti going around. And also once you know a framework, like say you know Ext Java and you know what operators you can call, it becomes super quick to write super complicated and complex code. The cons are that there's typically always a domain-specific framework that you need to use, and that the state and the behavior happen somewhere else. So if you're busy debugging something, you'll read through the declarative part, and then you'll still need to go back to the place where the state, if there's a problem with your state, or there's a problem with your behavior, you still need to see, you might need to look in two different places. Now, this is more or less of a con, depending on how you like to work. And then the third con I could think of was that there is always some other kind of learning curve. So say, for instance, you start using something like Ext Java, until you know all the operators that you can use, it's actually quite slow because there's another framework that you need to learn before you can start using it. So now let's come to object-oriented. Now this one I was most comfortable with because I'd been coding Java for a long time. But I didn't really know why, or where, or how this happened. And so the definition of this is where you encapsulate the state and the operations inside objects that support inheritance. So if I'm looking at the paradigms, the two big ones are, there's imperative and declarative. Now, object-oriented is, in fact, an imperative style. It's an imperative paradigm. It's not a declarative one. It's an imperative. It's categorized as an imperative paradigm. And I think the first language was Smalltalk that was using that. I can't remember the dates of that, but that I think is probably late 60s, early 70s. That's about the time, even though the previous languages were speaking about objects in the way that they were talking about the language, there wasn't really a language that supported having objects as such. And on the right-hand side, again, a little sample from Kotlin of what it would look like if you're reading object-oriented code. So there's suit, it's an enum, it's a class. I've got a suit card class that's got some state in here and some behavior, and it's inheriting from this playing card object. So in a diagram, what happened here? We had all of these commands that we had in the first slide, and we had the big blue state cloud. And so what object-oriented does is it splits it up. It says, we're only going to have the behavior and the state that work together, and none of the other things in one object. So that's why I've done this boundary over here, so that these round-cornered boxes would be the objects. And then there's this concept of inheritance. So this object has access to this state and this behavior, but this object does not have access to this state and this behavior. And what are we doing? we're just splitting things up so that we can understand them and grasp them. So we're splitting things up into objects, and it's just a kind of a scoping mechanism. Now, when this goes down to the machine language, it's still that big spaghetti thing with a big blue cloud, but that's okay, because computers like that. It's like it's the humans that don't want to read all of this. And so this scoping mechanism protects us from ourselves, protects us from writing and accessing variables in places that is not related to the object. So what can we have from Kotlin that can support this? They've got classes. They've got this special data class, which I really like. You can make this data class in just one line, just like this. And the compiler will auto-generate for you the hash code methods and the equal methods and all of the getters and setters, because it knows that that's what you want from this data keyword. We've got enum classes. We've got interfaces. And then the inheritance we do with an abstract class like that. There's another class. You define it as open if you want some other class like this joker to be able to derive from suit card. And here's suit cards deriving from playing card. It gets the point value from the playing card, so it can access the state in the parent class. And then there we've got some state and we've got some behavior. And then how do you create these objects? Notice no new keyword. You just call it like this or like this, setting the parameters like that with some named parameters. And then you would use it like this. There you would get the behavior of the object. Okay. Pros and cons. It's easy to understand. Now, I guess I have a bias because I worked in Java quite a lot, so the object orientation was easy for me to understand. But the other thing is people know about objects. They know about things like a light switch that can be on and off. And so it's, in a way, it's easy to conceptualize things like that to tangible objects. And also we're separating out the state and the behavior. So it means that that particular object only has its state and behavior. So that would be the pros. The cons are that in the world of computers, everything isn't an object. And if you can only have objects, then you get these weird objects like composition, manager, implementation, owner, like a whole lot of strange objects that get created just because the language is enforcing object-oriented paradigm on you. Typically what you find are these text-util, string-util classes, and all that they have in are like just functions, which are just like utility functions, but they're packaged inside an object just because you can't do anything else. And then the other thing to know about object-oriented is every time you create an object, there's obviously some overhead in allocating the memory because an object needs some memory. And so if performance is a thing for you, you need to be mindful of where you're creating these objects and how you're using this, and places where you might need to rather use a primitive instead of an object because you might take a performance hit. So now functional. So you see now this is red because declarative was red, and functional programming is in fact in the paradigm of declarative code. So the bare bone definition of functional is, in lieu of assignments, use procedure calls to bind variables to values so that differential transparency is preserved. Blah, very complicated. What that means is if you've got, say, A equals 4, you can swap out the 4 for a function. That's all it means. It means anywhere where you've got a value, you can put a function in there. And this is a little sample of what functional programming would look like in Kotlin. I've got a function here, and here I'm using the underlying, remember I said declarative had an underlying framework that you were using? So in this case, this is functional, and the underlying framework that I'm using is the standard libraries in Kotlin. So I've got this deck of card, which is a list of these objects. I'm filtering. I'm passing in a function. Remember I said that if there's only one, if the function is the last parameter, you can pull it out in curly braces like that. This filter function returns this list again. I can map over this list, pass in another function, and then I can do the last value over here. And here, this function returns a single value, which I can then, which this function will return. So I could go something like A equals score jokers, where you can see it's a value that I'm assigning, and I'm swapping in a function instead of another value. So what pattern matching was happening here? So if you read a whole lot of imperative code and you kept seeing this. You kept seeing 4 running through the list, do something with it. Another 4 running through the same list, do something with it. Another 4 running through the same list, do something with it. So for functional programming, the looking at the code and finding the piece to extract wasn't those commands that looked similar and put them in a procedure. It was, in fact, that this is the similarity. I've got these 4 loops that are there, and it's only this piece of code over here that changes. And so what does that look like in functional? It looks like that. I've got a list, and I've got one method, which is map, which replaces all of those 4 loops, and all I'm passing in is just a function with the pieces that are different. There's another thing about functional, this particular map call and the standard library is this map call returns a list again, which allows you to chain. You can chain multiple calls because this method returns a list again. Whereas in this example, this 4 doesn't return a list. You have to go fetch the list out of the big blue cloud again before you can run the next list on it. Okay. There's my picture. The other thing that's important about functional languages is this concept of a pure function. So if it's a pure function, remember when I had the picture at the top with the procedure, and I said you could do it 2 ways. You could either let that procedure read the main memory, or you could pass the parameters in and then get the parameters out. If you're passing the parameter in and getting the parameter out, that's a pure function because you're not changing the global state inside that function. But what that actually means is that if you want to chain these functions together, you do need to make a copy of the data. So the data is immutable. You get some value coming in here, and the data gets transformed here on another copy. Another function gets called, and it gets transformed, and it gets transformed. And the other thing about a pure function is the side effects. They happen on the side. If it's a pure function, it should not have any side effects. Again, it's a way for us to split so we can understand, so we can zoom in. So I think Vincent said they had small methods that only do one thing. Now that works for us for mentally to understand how the code works, is to have a small thing that does only one thing. But the question is, how do you split it? Where do you cut the boundaries? And in functional, they're saying all side effects are out and we're not mutating any of the data inside. So the first thing that you need in a functional approach is you need to be able to have a top-level function so that you don't have a strings util class, so that you have a function at the top that you can just call. So in Kotlin, that's really easy. You just put it in a file, you just declare your function, and then you just do what you need to do. So here you can see value coming in, it gets mutated, and it just goes out. The other thing that you need for a functional language is functional types and lambdas. Now, this piece of code we saw a few slides back in the declarative slide. And what you mean by functional types is that very thing where you need to be able to pass a function into the object, into the function. So you can have a function as a parameter. So here's that syntax again. This says this transform is a function that takes an integer and gives back an integer out. This is also called a lambda. And then this is again how you would call it, and there are the curly braces on the outside. Then there's this really cool feature about Kotlin that I really like, which is called tail recursion. Now, if you have a function and you call the same function again and you call the same function again, if you do that long enough, you're going to blow out the computer memory, because every single time you call the function, it needs to push variables on the stack and push variables on the stack and push variables on the stack, and in the end it runs out of memory. Now, what Kotlin has, it has this keyword that says tail rec, and what it is if you write a function and the last thing you do, or the last thing you return out of the function is the same function again, if you put this keyword, the compiler has an algorithm that will optimize this code into an endless while loop or something. It knows how to unpack that so that it doesn't need to push those variables on the stack again. So you can write recursive functions without it blowing out the memory if you keep this structure. Pros and cons. Now, functional programming, it's really good for data streams. It's really good for if you don't know how big the data that's coming in can be, and it can actually be infinite, or you don't know like how many click events are coming through. It's like an endless stream that has no beginning and end. And then what you want to do is you want to take each piece of the stream and you want to transform the data with a series of functions. So that's what the functional program is really good for. It's also good for extracting little pieces of reusable algorithms. So that's the areas where that would be the pros that I could identify. And then the cons are that it can be complex because you need to know about the underlying framework and you need to think about things differently. If you used to, like me, for me it was complex. If you're thinking about if you're used to thinking about objects or you're used to thinking about imperative code, then that switch can sometimes be a little bit uncomfortable. And then there's this thing about the immutable objects that get copied. And so it could mean that if you're calling the functions and you have a lot of objects that get copied over, that you pay the price because there are going to be more memory allocations. Now, it depends on what area and where you're running this functional code. If you're running it somewhere on a very memory constrained environment, this might be something to look out for. But if you want the mental ease of dealing with the functions and you're prepared to pay the price of the memory allocation, then that's an option. But now, the real world. So this is a diagram of an Android app. I'll walk you through it. What you typically could have is you could have some other declarative framework sitting in the front here, Jetpack Compose, building my screen, getting in state from here, passing state out here. Here I'm in the Android framework. I've got objects, I've got activities and fragments built like this with some pieces of state living inside some of the fragments and some over here. I've got some state of the code that's actually living outside on the internet. This is coming in. Maybe I've got some data flows or some other RX Java or some way of pulling this data in. And here I've got some functional code. So I've got functional code feeding into my objects, feeding into a declarative system. And so you see, you can't actually have just one paradigm. In the real life example, that's not how it works. And the other thing to notice is we still have these blue clouds and these lines of commands sitting everywhere. So somewhere there's going to be some little small piece of imperative code sitting in somewhere. Even if it's not in one big spaghetti, it's still there. And underlying, when you compile it down, you're going to compile right down to that big imperative machine language underneath. And so here I'm going to end off with a quote by Roman Elizarov. Who's Roman Elizarov? He's one of the creators of the Kotlin language. And I'll pause for a moment, and you can read it if you like. And then I'll just say the last sentence. He said, "We are here to solve problems developers face day to day." So Kotlin is not taking a stance. They're not saying you will all code in objects or you will all use only functional programming. It's giving you tools so that you can go and look at the problem space, look at the domain, and figure out what is the best way for you to break down the complexity so that you can understand it. And then there will be something in Kotlin that's going to make your life easy to code it up like that. And there's some resources. I'm going to share the slides. These are all links, but this is just Wikipedia, right? Wikipedia for all of these things. And this is just straight the Kotlin docs on kotlinlang.org. And as a bonus, that's what the code looks like when the tail recursion function gets converted by the compiler. I thought it was pretty interesting. It makes this while true, which is because it doesn't know how many times you're going to jump inside the code. And then it's got this variable, and then it's got this switch, and this break here will just make it loop again, I think. And this continue, oh wait, no, the continue will make it loop again, and the breaks will break out. And then if it breaks out, then it returns and breaks out of the while loop, boom, and comes out of the function. Cool. Okay. How am I doing for time? I don't actually know when I started, so questions. No computer science questions, because I won't be able to answer those. Or, if you have a computer science question, I have to Google it and then answer it on Twitter. No?
So I don't have a question, I just want to testify that we started using Kotlin like 1.5 years ago at our company. I didn't know that I was using functional programming, thank you for that.
Yeah.
But most of those methods and things we were using. And for example, there was a class, for me it's the biggest advantage is the size of the code. So there was a class that we reduced more than 60 or 70 lines from Java to Kotlin. So it was really good, and anyone that wants to use it, it's really practical. Of course, you need to adapt your mind. It's a different mindset for a lot of things. Like, hey, I can chain methods now. I don't need to be so declarative. I can do things the other way around. But it's really good. Thank you for that.
Yeah.
Is there any reason to try a pure approach, either declarative or functional or anything like that?
From a practical point of view, I want to solve a problem. And I'm kind of like that. The way I do it is like I try and find the best solution. Now, let's say take something like pure functional. If you take something like Haskell, right, you can do things in a pure functional way. But if I'm writing code for a user, I don't know if I can actually write that all in Haskell. And there's the other thing about the side effect. You need to be able to because the whole of that Jetpack Compose screen, it in fact is making a UI, which is in fact a side effect. So you can't escape the side effects. So from a functional point of view, to keep that pure and eschew all side effects, you're going to have some algorithm running somewhere in your computer, and then it's not going to have that much use. So I would personally opt for what fits into my brain. How can I make it understandable? And what fits into the Maia in 6 months' time? Because in 6 months' time, I'm not going to have had any clue of why I decided on these variable names and putting things together. So I don't know, maybe I think, okay, there is a benefit. If I want to learn things, say I want to learn how to do this in a functional way. I want to learn functional. And I'm going to tie my one hand behind my back and only write functional. I'm going to struggle, but I'm going to learn. So I would say I would use it as a learning opportunity and set myself problems to try and keep things pure, rather than, I guess maybe I'm a bit more of a generalist and less of a purist in that sense.
I agree. I was just curious because I don't think there is any way, besides you go pure imperative, there is no way that you can't use a blend of the different approaches.
Yeah.
In my experience, I find that I try to isolate the stuff. So, I mean, there's value in,
Yeah.
so I mean, for me, there's value in pure functions because they're isolated, you can test them, and you park them. When you take that pure function and you put it inside of a class, then you've now scoped it, but now you have to be careful that it doesn't touch other stuff in the class and escapes the scope of the function. So it takes discipline to keep the paradigms separate. But eventually, I believe that it allows you to minimize the cognitive load. So functional programming is a way of isolating certain things, minimizing the cognitive load. Object orientation is a way of grouping things to minimize cognitive load. So, but if you take all your functions and you put them in a class just to group them, you need discipline so it's always a balance. But in my perspective, Kotlin is the language that makes it the easiest to maintain that discipline, and it will guide you. So it will suggest, hey, you've made this thing a bar, but you're not actually modifying it, so make it a val, so that if you do it by accident, the compiler is going to warn you, because the earlier you find out about it,
So excuse me, we live streaming, so with questions, right? We need to speak to the mic so that they can hear the questions.
Another example of how that fits in is something that's declarative that we use quite often is SQL. So there you're describing exactly what you want the database to give you. And if you've ever, anyone's ever tried doing something, you can do it in SQL to do like steps for very specific things, but it's awful. And that's why we maybe retrieve from the database in a declarative way and then transform in our code in that more stepwise.
I wanted to use SQL as an example, and then when I went online and had a look, there was this huge fight where people were saying that SQL isn't purely declarative, and I thought, let me just step out of that one and not provoke it, but I'm glad you mentioned it. So I also thought it was declarative.
It's not purely, but we use like when you use it.
Okay.
It's primarily declarative.
Primarily. There's a backdoor.
No, if you look at most SQL is.
Wait, you need to speak into the mic. They don't come in.
So most SQL can be very declarative, but then you set up PL/SQL, and then you can write very imperative code, and it does not reduce the cognitive load of the people who come after you. So that's why I mean, when I see a system that's composed of hundreds of stored procedures, then I just run.
One last question.
Okay, I'm going to disconnect.
Thank you, Maya.
Yeah.